Welcome to this podcast, and thanks to our guest who is in the studio today. We're going to be discussing an editorial from the journal Clean Technologies and Environmental Policy. It explores the really critical role of process systems engineering, or PSE, in this huge global shift from carbon-based energy towards a hydrogen economy. So today, we're doing a deep dive into something absolutely central to our energy future, this massive global transition away from carbon, looking towards hydrogen. Now, it's a colossal undertaking, right? Often talked about in broad policy strokes or, deep scientific detail. But what happens when we look at it through a different lens, a unique one maybe, often overlooked, that of the engineer? And that's exactly what this fascinating editorial brings to the table. So our mission for this deep dive is pretty clear. Policy gives us the big picture, the vision for these huge shifts. But the practicalities, the actual nuts and bolts of engineering, they're absolutely critical. And, well, sometimes they get a bit pushed aside, don't they?
We're going to unpack the key insights from this editorial, try to clarify some of the complexities involved, and maybe reveal some surprising facts about hydrogen's real-world role all through that crucial engineering viewpoint. Okay, let's unpack this. So let's start with the big one, decarbonization. It's this massive global challenge. Science has made the need pretty clear, and that shapes policy. But here's something the editorial really digs into. Policy has to consider the practical, real-world stuff that engineering deals with. Sort of a constant negotiation, isn't it, between the grand vision and what's actually doable on the ground?
That's a perfect way to frame it, yeah. The editorial uses this really interesting analogy. It talks about policy like a cascade control strategy.
Okay.
So think of it like this. You have your main goal, the master climate goal, maybe reducing global warming overall.
Right.
And then you have something that reacts faster, like the carbon intensity of the economy. That's the slave variable. The master controller policy sets the target for that faster variable.
Makes sense.
And this is the key engineering insight when you're tuning these policy actions, you just can't ignore all the other ripple effects, things like energy prices, energy security, even, geopolitical stability. These aren't just side effects. They actually feed back into the system and affect whether the policy even works.
That really highlights how interconnected everything is.
Yeah.
So given these really tough decarbonization targets we're facing, how does process systems engineering, PSE, how does it actually help manage what the editorial calls this complex industrial metabolism?
Yeah.
That whole interconnected system of energy and materials. It's under huge pressure. And if we look back, historically speaking, engineering has always been kind of the hidden engine in energy transitions, hasn't it?
Oh, absolutely.
Moving from wood to coal, then oil and gas.
Yeah.
It wasn't just about finding the stuff. It was about the engineering needed to make it practical, dense enough, easy to transport. Technology had to keep pace.
Precisely. And that history is important because the editorial points out something about our current shift to renewables. It suggests that policymakers, well, they launch these big initiatives, definitely backed by science, but maybe sometimes disregarded some engineering aspects.
Right.
What seemed to happen, according to the editorial, was this quite sudden jump from using carbon-based hydrocarbons straight to non-fossil electricity, mostly wind and solar, maybe bypassing some intermediate steps or considerations.
So what are the implications of that jump? What does it mean for us now? The editorial seems to argue pretty strongly that just relying on electrification alone, well, has limits.
Definitely.
It's not like you can just plug everything in,
Yeah.
especially in those really capital-intensive sectors that are hard to decarbonize. Think heavy industry, long-distance shipping, aviation.
Exactly. And then there's the inherent challenge with wind and solar, the variability. Supply doesn't always match demand. So the editorial argues it's nearly impossible to satisfy the entire rapidly growing energy demand globally if renewables are the only path we're really pushing hard.
Right. So that variability, that's where hydrogen starts to come into the picture.
That's exactly it. Hydrogen emerges as a really important potential solution, especially for storing energy. You can use electricity, ideally renewable electricity, to produce hydrogen through electrolysis. The editorial calls this an indirect form of electrifying the industrial metabolism.
Okay, so using electricity to make a storable fuel.
Essentially, yes. But the crucial point the editorial makes is that these low-carbon policies, they really picked up speed before the engineering side had fully developed and scaled up the economically viable hydrogen technologies needed to actually meet those ambitious policy goals. There was a bit of a mismatch in timing.
Which leads us right back to process systems engineering. The editorial positions PSE as the framework specifically designed to handle this kind of complex systems integration. It's not just about optimizing one thing in isolation, is it?
Not at all. It takes this multi-criteria view. So you're trying to improve profit, energy efficiency, use materials better, but at the same time, reduce carbon intensity, water use, even impacts like land use change.
Mhm.
It's about looking at the whole system, all the
A
trade-offs.
truly holistic approach, then.
Indeed. And PSE, especially combined with digitalization, becomes crucial for managing energy effectively. It's about balancing supply from all these different sources with demand from various users, and really importantly, figuring out the best storage options to keep the supply secure and reliable.
Like managing a really complex grid.
Exactly. And we've seen moves in this direction, particularly in Europe. They specifically talked about power to hydrogen pathways, even planning to repurpose natural gas pipelines for hydrogen. That's a clear signal of shifting from just a general low carbon economy idea towards a more focused hydrogen economy.
It sounds potentially very powerful, but is there a risk of seeing hydrogen as, the one silver bullet that solves everything?
That's a great question. And what's really interesting is that the editorial directly challenges that silver bullet idea. It argues quite strongly that the economic and environmental benefits could be much better, significantly enhanced if solutions were engineered in conjunction.
Meaning combining different strategies.
Precisely. Like integrating CO2 recycling, whether it's from fossil fuels or biogenic sources, using carbon capture, utilization, and storage alongside those electricity to hydrogen routes. They give a specific example
Oh, yeah.
from Caudle and colleagues in 2023. It's a sodium chloride-based mineralization process. You capture CO2, say from a gas power plant, combine it with brine electrolysis using renewable power, and you co-produce useful things. Sodium carbonate, chlorine, green hydrogen, and even supercritical CO2, which could be used for enhanced oil recovery. It's about creating value from multiple streams.
Wow, that's finding synergy in unexpected places.
It really is. And another example they mention is e-methanol production, highlighted by MNES in 2024. Here, you take captured CO2, maybe from an oil refinery, hydrogenate it using green hydrogen, and produce e-methanol. The big target there is using it as marine fuel to replace heavy fuel oil.
So these aren't just isolated fixes, they're integrated, engineered solutions.
Exactly. That's the core argument. Combined solutions offer a much more robust and potentially efficient path forward than just focusing on one technology alone.
Okay, so hydrogen has promise, especially within these integrated systems. But the editorial also flags some overlooked challenges. One big one seems to be the basic practicality, the prerequisite of transport suitability and safety. It's not trivial to move hydrogen around.
No, it's not. And this brings up a really important point about the energy toll involved, which is often perhaps underestimated.
Energy toll.
Yes, the energy penalty you pay at each conversion step. Think about it. You use electricity to make hydrogen. Then, to transport it easily, you might convert it into something like a liquid organic hydrogen carrier, basically an oil that absorbs hydrogen, or into ammonia.
Right.
But then at the destination, you often need to convert it back into hydrogen to use it. Each of those steps uses energy. The editorial makes a crucial point here. Energy efficiency, a primary process performance indicator, has been undervalued in the push towards these molecular energy carriers.
So it's a whole chain of conversions, and each link costs energy. This really challenges that idea that if the initial energy is renewable, then efficiency downstream doesn't matter as much.
Exactly. The editorial argues against that kind of simplistic approach. Overlooking these energy tolls isn't just inefficient, it can have knock-on effects.
What kind of effects?
Well, these inefficiencies create snowball effects across industries. If one process needs more energy input because of conversion losses, that demand ripples outwards. And there's another significant environmental angle beyond just carbon.
Okay.
When you scale up solar and wind to the massive utility scale needed for cities and heavy industry, the environmental footprint isn't zero. You need huge amounts of raw materials to build the panels and turbines, and the land use changes for these enormous energy farms can be quite significant, potentially leading to environmental degradation. It's a trade-off that needs careful consideration.
Right. It's never quite as simple as it first appears. Let's shift gears slightly. Where does hydrogen fit in today? The editorial mentions its main uses are currently in oil refining and making ammonia.
Yes, and ammonia is a really interesting case study within this. About 80% of the world's ammonia goes into making fertilizers absolutely vital for agriculture. And traditionally, it's made using steam methane reforming, SMR, which uses natural gas and releases a lot of CO2.
That's the gray hydrogen process, right?
Exactly. So there's a big push globally to decarbonize ammonia by replacing that gray hydrogen with green hydrogen made from renewables via electrolysis. But let's look at the energy involved. Making ammonia itself takes about 9.7 megawatt hours per ton,
Right.
but producing the green liquid hydrogen needed might take around 11.7 milliwh per ton just for compression and liquefaction, on top of the roughly 55 milliwh per ton of hydrogen needed for the electrolysis itself. And then you've got things like boil-off loss with liquid hydrogen, where some just evaporates during storage and transport. It adds up.
Okay, let's unpack this. Those energy numbers are quite
Yeah.
something. So, given that, the editorial reaches a pretty strong engineering-oriented conclusion, doesn't it, about cracking ammonia back into hydrogen?
It does. The conclusion is that cracking ammonia, splitting it back into hydrogen and nitrogen just to supply hydrogen doesn't really make sense from an overall energy efficiency perspective, especially when ammonia itself has direct uses, including as a potential fuel, and it's already a huge chemical commodity traded globally. Why add another inefficient conversion step?
Right, if you've already got the ammonia.
Use the ammonia. Or the editorial suggests looking at other routes. Things like gasifying heavy oil fractions or reforming natural gas, but crucially with carbon capture integrated. These methods can tap into the hydrogen already present in fossil fuels and direct it towards useful things like making methanol by recycling captured CO2.
So using the existing resources more cleverly with CCS.
Precisely. And it's worth remembering this blue hydrogen from fossil fuels with CCS isn't entirely new. The underlying technology, CO2 pre-combustion capture, was understood well before the recent sort of hydrogen hype really took off. Some of these solutions have been around, conceptually at least.
That's important context. Okay, we've talked engineering, we've talked efficiency,
Sure.
but inevitably it comes down to cost. The editorial mentions marginal abatement costs, MA. How do those factor in?
MA is a really valuable tool for policy. It basically tells you the carbon price needed to make a particular low-carbon technology cost competitive with the existing high-carbon one.
And what do the numbers look like for hydrogen?
Well, estimates cited for Martin and colleagues in 2022 put the cost for hydrogen fuels quite high, between €530 and the 1,345 per ton of CO2 avoided back in 2020. Interestingly, trucking came out lowest at €530 per ton.
Why trucking?
Mainly because diesel trucks are so carbon intensive to begin with, switching to hydrogen avoids a lot of CO2 for the cost incurred. For ships, using ammonia looked potentially viable around 538 per ton CO2 by 2030, and for aviation, using e-fuels was around 788 per ton CO2.
So quite high costs across the board.
Yes. What these figures strongly suggest is that for hydrogen to really take off in many sectors, it's going to need pretty hefty government subsidies, maybe over 3 per kilogram of hydrogen, or really high carbon prices, perhaps upwards of €200 per ton of CO2, or likely some combination of both. The economics aren't straightforward yet.
That paints a challenging economic picture. But the editorial also adds a nuance, a counter-argument, to focusing only on those production or abatement costs.
It does. Citing Weichel and colleagues from 2021, it points out that just looking at production costs ignores a lot of real-world factors. Taxes, company profit margins, the huge costs of R&D, marketing, all the things that shape actual market prices.
It's like in the oil and gas world?
Exactly. Prices there aren't just based on the cost of drilling and refining. They're heavily influenced by market dynamics, strategic decisions, perceived shortages. So this leads to a really big open question for hydrogen. Will we see a truly global market develop, like for oil, where prices tend to even out worldwide? Or will the high cost of transporting hydrogen mean we end up with distinct price zones, like we see with natural gas, where prices in North America, East Asia, and Europe can be persistently different? How that plays out will have huge implications for trade and energy strategy.
That's a critical question hanging over the future. Now let's zoom out again to the really big picture. The editorial stresses that basic things like energy costs and energy security are major factors currently holding back the broader energy transition. We've certainly felt that with recent global events and inflation.
Absolutely. And if we connect that to the bigger picture, the editorial points to this growing, slightly worrying gap between rising global energy demand and how fast renewable energy supply is actually expanding. This mismatch can easily feed into perceptions of instability.
And this creates other dynamics too.
Yes, what the editorial calls the hidden dynamics of shifting energy power. As the world moves away from fossil fuels, the nations that currently dominate the energy landscape might find their influence waning. But because renewable resources and the ability to harness them are distributed differently around the world, it creates opportunities for new players, new nations, to emerge as major energy leaders. It's potentially a massive geopolitical realignment.
A fundamental shift in power. And we're already seeing policies that seem to reflect this strategic thinking, aren't we?
Definitely. Look at the U.S. Inflation Reduction Act, explicitly framed as key to redefine American leadership on climate. Or the EU's Carbon Border Adjustment Mechanism, the CBAM. That's designed to protect EU industries, but also to prevent emission shifting, basically, stopping industries from just moving their pollution elsewhere. These are strategic economic tools as much as environmental ones.
Right, they're shaping markets.
Precisely. These policies act like a control loop, influencing prices, investment decisions, trade flows, all within this.
What a fascinating and frankly complex picture this editorial paints. Our deep dive today really shows the transition to a hydrogen economy isn't just about switching fuels. It absolutely demands that holistic, engineering-focused approach, the kinds of process systems engineering offers, to actually optimize these incredibly complex systems, ensure we're being genuinely efficient, and integrate solutions smartly. It's about understanding that whole industrial metabolism. So as we wrap up, here's maybe a final thought for you, our listener, to consider. How do we make sure that this huge, ambitious push for decarbonization, especially looking towards hydrogen, consistently weaves in the kind of rigorous systems-level analysis that PSE represents? How do we do that effectively to avoid accidentally creating new environmental problems, paying huge energy tolls, or building unsustainable economic models? How do we truly balance those vital climate goals with the messy, complex realities of our global industrial metabolism? Thank you so much for your participation today. It's been incredibly insightful. Goodbye.